All right. Happy to have everyone here virtually for our webinar today. We'll get started. So welcome. I'm excited to introduce Gecko's newest technology advancement in NDT robotics, Tri-Lateral Phased Array. I'm Troy Demmer, the co-founder of Gecko Robotics. And over the past 5 years, Gecko has really changed the way that we approach the industries we serve today. Many of you are from the oil and gas industry, but we serve many other industries as well: power generation, pulp and paper manufacturing, even the Department of Defense. And it is our mission to partner with our customers closely to develop solutions that help manage your most critical infrastructure, creating a much more safe and reliable and predictability around your most critical assets. So today we're going to go through a presentation, and all the attendees will be muted, but I want to be sure that you know that you should be asking questions. We want to make this interactive and ensure that the content is most relevant to all of you that are joining today. So if you want, you can submit your questions down in the Zoom box. There's 3 ellipses and a more button, and under that there will be a Q&A located, and you can type your questions in there and we'll actually take them in real time. So with that, I'd like to introduce our presenter and Director of Operations here at Gecko, H₂S David. H₂S has been in the NDT space, serving these industries for the past 10 years, and he has extensive knowledge and experience working with customers to improve their mechanical integrity programs with a focus on special programs and RBI implementation. He's an expert in robotic solutions in all these industrial industries that we've spoken about. He's worked across the globe, and he's going to take us through the details of the newest advancement that Gecko's created called Tri-Lateral Phased Array. So with that, I'd like us all to welcome H₂S. H₂S, take it away.
Thanks, Troy. Thanks everybody for joining. We'll jump right into it. Today's agenda, we're going to cover a brief history of the ultrasonic technology for the industrial space in relation to the in-service inspections, mostly around damage mechanisms related to wet H₂S damage. Today, that's specifically what we're going to be talking about, but there'll be a little mix of corrosion applications and others as examples. We're going to talk about the types of technologies around this to be able to use these things with robots and create a more productive inspection, far more productive as far as getting access to the locations. And we're going to understand the pros and the cons of trying to implement phased array where conventional UT is the norm. And then I'm going to show you some real world examples where we've used this today. So brief history about the way this work's been done in the past is traditionally scanners are used with conventional ultrasonics to do corrosion mapping. And we're going to briefly just talk about corrosion mapping to start, and then we'll work into damage mechanisms. This helps set up kind of the overall evolution of the technology. So with conventional ultrasonics, we have generally a 1/4 to a 3/8 inch probe. It's a dual element probe. These are generally stepped somewhere around 200 thou by 100 thou for indexing resolution. They have kind of a slow scanning speed. You can move them 6 to 10 inches per second, but overall rate of production somewhere less than 100 square feet per day. They're restricted by the data throughput and file sizes overall. These conventional systems generally are non-steerable mechanical scanners. So you put them on the surface and you drive them. You scan maybe 2 foot by 10 foot, and then you bring that scanner back to you, you pop it off the surface, you move it down to your next location, and you start your next scan maybe 2 foot by 10 foot. So it's a very manual process as far as moving the scanner. And then you need rope access or scaffold to get it into the required locations. What we're going to talk about today is enabling phased array to be a more productive tool for this type of technology or this type of inspection methods. And then also we're going to talk about using robotics to get access to the locations that we need. So phased array, just a brief thing about phased array is that it's, to sum it up, is multiple probes in a single housing using electronic delay lines to hit those those elements to create focusing, steering, and overall large aperture to work with. You can use either linear probes, dual linear probes, matrix arrays, and a combination of a wider range of frequencies. The larger the active aperture is of the probe, the higher the productivity can become, especially in 0 degree. We have the ability to use electronic focusing, and it can be adjusted through the depth. So if we're working with a 1/2 inch material, we can adjust the focalization for that, for the depth that we're interested in, the region that we're interested in. If it's 1 inch or 2 inch, we can adjust the focusing for that, provided that we have the right probe and setup. And in this case, we're going to be talking about using electronic and passive focalization today to increase the probability of detection. All of this together provides a very high resolution imaging option for doing damage mechanism reviews. So here is on the bottom, we have the 3/8 probe doing conventional ultrasonics. So the probe is moving a 200 thou by 100 thou. And then on the top, we have a 1 1/4 inch probe that's moving roughly 1 inch every time that it strokes. So there's about a 5x difference in the overall speed of the system, reducing 5 raster movements that don't need to happen. Overall, with the traditional AUT that's down below, you have what's common is somewhere around a 200 thou by 100 thou resolution. This gives us roughly 50 readings per square inch or 7,200 readings per square foot. It takes roughly 30 minutes to go 2 foot by 10 foot. So it takes quite a long time to make some progress in a given shift. I've seen these systems also used at a 1/2 inch by 100 thou, creating not really a square image, but you can get a lot of production that way. So you can go about 2 foot by 10 foot in about 15 minutes, but then you're not getting 100% coverage. And then also the data that you're getting creates an image that isn't square, it's more torn in one axis, and it's not good for using for fitness for service. So as you reduce or increase the indexing down below a 1/2 inch to 200 thou or 1/4 inch or less, you're going to increase the time that it takes to get that imaging done, but overall increasing your resolution. Now with the phased array option, we're doing a millimeter by millimeter coverage, which is 625 readings per square inch, and it's 100,000 readings per square foot roughly. This takes 6 minutes to make a 2 foot by 10 foot scan, providing 100% coverage. And you can see here that we just made roughly the images aren't synced here. The one on the right made a 3 foot scan. The actual video on the left is doing a 5 foot scan, but you can see that roughly it's 5 times faster, and it enables you to go ahead and start looking for any type of damage and start doing your review as soon as the scan is stopped, versus the older conventional method is going to continue to go, and it's going to take drastically longer to get those scans done. Okay. So that's kind of a precursor to what we're going to talk about today. We're going to apply this technology for trying to find wet H₂S damage. So going from conventional to what we call rapid AUT, applying a phased array to do the things that we were conventionally doing with the conventional UT, we can also use it for doing wet H₂S damage, but we need to add in multiple other things. So let's talk a little bit about wet H₂S damage. It is a common problem in the oil and gas petrochemical manufacturing industries. It can occur with a carbon steel equipment that becomes exposed to wet H₂S service environments and can come in several different forms. The wet H₂S corrosion can be particularly dangerous form of corrosion because the damage is caused and takes place in the interior of the vessel and can occur without warning. There's no corrosion generally at the ID of the vessel. This is happening internally. It's very hard to detect. You have to use some type of volumetric method, such as ultrasonics. The only time you're going to see this is when you have that blistering that's on the right, and you do a visual. You get inside, you do a visual, and maybe you do mag particle to look at those blisters and see if you have any periphery cracking or ID landing cracking. So we need to use a volumetric method to go find these type of damages, especially the HIC, SOHIC, and the sulfide stress cracking. And to do that, we can use that phased array application, but we also need to add in an angle beam method to accomplish that goal. So here is the industry standard of the way that this work is currently done. It's often called a tri-element or a triplex technique. These probes are essentially the same setup that we were looking at earlier with conventional ET, except you're adding in an angle beam set. Oftentimes you're getting a 45, and a 0 degree. And you're going to want to get that 45 in either in both an axial and circumferential direction. So here in front of us, we have a what's very typical is you got a dual element UT probe, and then you have your 45 in one direction and your 45 in the other direction. This allows you, with it being in one beam and in one housing, to capture all this data in one go. But you use the 0 degree to find laminations and occlusions, and then the angle beam to look for periphery cracking, stepwise cracking in that axial and circumferential directions. There are many advantages to bring all these groups together to provide one inspection pass to find damage. However, being that its underlying technology is conventional UT, there are many drawbacks, such as lateral resolution, index resolution, the production per shift. It's a fairly slow gathering process for scanning the area. Overall, it generally gets somewhere between 80 to 120 square feet per shift. Let's dive in a little bit about what that data looks like. Most importantly, the larger issue of the technology is the lack of the data density, and the lateral resolution is very poor. It creates poor imaging resolution. This is magnified by the lack of the focusing, often out of focus for the range of material that you're looking at, whether that's half-inch material or 1 inch or 1.5. Oftentimes that focus is either beyond or too early in the beam set to be able to accurately do the imaging. This creates fuzzy imaging that often leaves the technicians needing to do further prove up, either through phased array or TFM. So there's a lot of drawbacks to it, as far as being very slow to produce the relevant scans that you need to produce. And then it always needs some kind of follow-up to make sure that you can see the periphery cracking, the stepwise cracking, or any ID touching cracking. So, all right, jump into the next one. So with trilateral, we essentially took that technique and we applied phased array to it. This was very challenging to overcome, trying to get those 3 beam sets all in one scan apparatus. But we essentially put 2 probes in a housing with the 3 angle beam sets. There's a 0 degree, a 30 degree, and a 45 fixed that's shooting in the lateral configuration. This having the lateral in the same axis as the 0 degree eliminates the need for several scans to acquire the 3 groups. This is often what was holding phased array back from being a good method for doing HIC, is that it took fairly long to get the data that was required, and you had to scan the surface many times to get the 3 beam sets essentially, and it often would take longer than doing tri-element, or at least the same time. So when designing this technique, we came up with three different versions of it. So we wanted to design 3 groups of the trilateral, one to help with curvature, so it has roughly a 2x speed over the tri-element method. And then we have the original design in the middle that's roughly 5 times faster than the older technology. And then we have a very large 2.5 large probe, very large aperture for doing 10 times the same speed. This is really good for doing like large assets, large vessels, or spheres. It can cover roughly 800 to 1,000 square feet per shift. It's extremely productive and very, very high resolution. So here we have some images of some data that we have that was a plate during prove out of trying to learn about what kind of resolution we could get from this technology. We were given mini plates by many of our customers that we work closely with and partnered with on this. And you can see here on the left that the trilateral, the B scan, and the C scan have a very, very high resolution. The B scan has a very high lateral resolution. Through depth is very, very high resolution. We're using 7.5 megahertz probe, which gives you a really very high resolution as well. And then on the right, you have the older method where the image is very pixelated, and the B scan is very challenging to see any type of, obviously we can see damage, but what we can't tell is stepwise linkage, periphery cracking, any ID landing cracking. Just looking at this data set would be very, very challenging to make any judgment calls about the condition of that asset. We would have to do some form of follow-up to be able to understand the condition of that asset. So here's that same plate, and here's just kind of a static image of it. This gives a really good idea of how good the imaging is, and you can see here there's periphery cracking along with stepwise cracking that's evident here in this plate. We have many samples that we've had with this that we've been able to prove out its ability to find the periphery cracking and stepwise cracking. This is just the 0 degree, and then on the next slide I'll show you some angle beam data as well. For the angle beam, we're able to very, very accurately size the height of the defects, the periphery cracking or stepwise cracking that may exist. We're looking exactly the same location as the previous slide. Here we have roughly a 1/2 inch tall vertical stepwise crack along with ID touching periphery cracking. And then what's really neat about the C-scan is that we can put this into a depth chart, and we can now see where the laminar tearing is, where periphery cracking is, and then where the stepwise linkage may be. So here you can see with the green areas that you have laminar tearing, and in the red areas you have the periphery cracking, and then in between you've got the stepwise cracking as well. So by having the high resolution data, we can now put it in a depth chart and very accurately screen a large area, 10 square feet, 20 square feet, and very quickly pick out the worst areas. Rather than looking at this in like an amplitude chart and trying to go through every single B scan, especially if we have a lot of hits, that can be very time consuming. Now we can put it in a depth chart and we can pick out some of the worst areas to really evaluate really quickly what is the condition of the asset.
Hey, Chase,
yeah.
We've got a couple questions that have come in here.
Sure.
One question is, do we require a splitter? And back to sort of your probe selection.
Sure. Yeah. So based on the setup that we're using 128 channels, typically using a 32-128 or a 64-128 system. So to connect those two 64 element probes, we're using a splitter. Yes. So we're using up all the available channels on our phased array instrumentation.
Great. And then another question, going back to the probe selection, we understand that there's different probes for production rates as different shapes and sizes of our spheres, upwards of bigger vessels can use a larger probe. How about for thickness? How is that something that we choose? What type of probes around different thickness of materials, or where we expect those flaws to be within that material?
Sure. So inside roughly 3 inches of material and below, we have a probe selection that is very adaptable to pretty much everything in between. Other than curvature, we would have to look at other forms for curvature. But when it comes to the overall element size, pitch, and whatnot, we have a good probe selection for covering materials less than roughly 3 inches. For going 3 inches or more, we would have to look into using a different aperture setup, using a different probe setup to take it further into thicker materials.
Excellent. And then one more question here before we can move on. Just attendee asked, is this better than TFM?
It's a good question. In respect to productivity, it's much more productive. We're using active and passive focalization within the probe set, and with the two of those, we have extremely high resolution imaging and the ability to do very fine detail sizing. I think it's nearly as good or just as good as doing most TFM applications, depending on thickness and overall constraints, but in respect to many aspects, it's much more productive than using TFM and nearly the same resolution as doing TFM.
Great. And we actually had one additional question come in. These have been great questions, everyone. What frequency ranges do you have?
Oh, it's a good one. Yeah, I think I skipped right over that, but in the 0 degree, our most common and what we'll use for most carbon steels is going to be 7.5 megahertz. So the 0 degree, 30 degree L wave probe is a 7.5 megahertz. That's our standard going forward, provided that it works for most materials. Surface condition and other issues maybe not allowed, but we've had a lot of really good success with using 7.5 meg. And then in the angle beam lateral probe on the side, it's 5 megahertz shear wave. Okay, so where we've used this technology so far is in various places. We've had it in the field since about May of this year, testing it at various sites with partners that we have in the industry. And the main goal is to, in most cases, do a non-intrusive inspection from the outside and look at the condition of the asset for any type of hydrogen damage. So in this case, we have a butane sphere here that we did roughly 3,000 square feet on. For this sphere, we did the bottom third essentially, and it was inside a dike, so we couldn't really use GLG very much. Rope access is kind of the preferred method if you're going to use typical scanners. But the conventional AET was roughly 30 shifts and far too expensive for the client to do such a project. So then it kind of lined up really well timeline with us releasing this product and them being interested in it, that we were able to provide the same work scope, same outcome at roughly 6 shifts. That was 3 shifts of the trilateral and 1 shift to doing the phased array weld inspection. We required no scaffold. We didn't use rope access, and obviously no GLG. The overall outcome on this particular vessel was that we achieved their non-intrusive inspection, but we did find significant damage that they were unaware of was there. Some hydrogen blisters with ID cracking or ID periphery cracking landing on the ID. Lots of mid-wall damage as well. But the main thing is we had that periphery cracking touching the ID. And that's shown here. They chose to go into that vessel soon after, maybe a few weeks or a month after. And when they opened it, you can see on the left, we had all the damage that's shown here in the C scans. And then in the middle, when they went inside, got in that manway, shined their flashlights out, you can see all those blisters that ended up accumulating. And this was all throughout the probably the bottom 20 feet or so of this vessel. It was all throughout. So lots and lots of blistering. Then they did wet mag and they were able to confirm that periphery cracking that was landing on the ID that we were seeing. And our next application of it, we did an SRU tower. This tower was some kind of stripper column of some sort, stripping off SO2 or H₂S. They also wanted to do a non-intrusive inspection prior to a shutdown. They wanted to get good insights into what planning they needed for the turnaround. We did 750 square feet with limited access. There was only 2 decks on the vessel, so we did everything robotically. The alternative was them doing an internal manual UT wet mag, and then by doing the inspection this way, it leaves really no time for the turnaround planning, requiring no timeline for them to be able to create repair plans and things like that. So by doing it externally, we were able to give them the insights they needed prior to that turnaround as far as the health of the vessel and planning out that turnaround. And we were able to do that in roughly half the time as the older method. Got one more.
Chase, I've got a question here for you. Going back to the sphere case study, were we able to size the cracking and damage before making entry into the vessel?
Yes, we were. A critical part of this technology is that over the triplex or tri-lat method, what we're trying to achieve here is the ability to see mid-wall damage, see laminations and occlusions, see whether or not they have damage. So, and then whether or not we have blisters or periphery cracking, whether or not any of that mid-wall damage is connected to adjacent damage that has stepwise cracking in either the axial or circumferential direction. We're able to accurately find all of that and characterize all of it. And then, yes, we can feed it into a fitness for service group or an engineering group, very high detail. We've done it several times, especially for that butane sphere. We did it There's a couple different ways to provide that information, and we've worked closely with engineering groups on how to provide that information, but we can provide the raw data for them to be able to make their calculations. The next case study that I have is a wet H₂S service tower. I believe this is an amine service. We did an external inspection to prepare for an upcoming shutdown again. This particular vessel had many inspections prior in several 5-year intervals prior, 2012, 2018, and then 2021, where blistering was found, but no cracking was found. And so in this case, the customer was interested, well, with 25x resolution, what could we do with that? Maybe we could find that there is significant damage here that's not being seen. And that's what we were able to produce here. So with the tri-element method, they were looking at doing 10 shifts of the base material inspections, and we were able to reduce that down to 3 shifts. On the next slide, I have some of the examples of that damage that we found here. I've gated out the back wall, so you only have kind of that gray background. Is there's no corrosion on this vessel, so completely remove the back wall. We're only looking at mid-wall damage, so all the mid-wall stuff is showing here in various colors in the depth chart, and all of this damage was somewhere between this vessel was 3 inches thick, 1,100 pounds of pressure. And this vessel had damage somewhere between 1.8 inches of depth all the way to the ID, stepwise cracking all the way to the ID, as shown there in that B-scan kind of rollout that we're doing right there. And then there was also several areas of the yellow that had damage between 2.2 inches to 2.8 inches as well. So various areas of damage that are kind of circled out here, and they're grouped up together based on the depth that they exist.
Hey, Chase, one individual asked if we could go back to the tower, the SRU tower.
Sure.
If you could just elaborate a bit on the findings or the outcomes of this inspection.
Sure. So the SRU tower, again, it was a non-intrusive inspection to get prepared for their turnaround. At this time, that turnaround hasn't came. This vessel was roughly 1 inch thick, I believe, and we had roughly a ½ inch of material loss around these downcomer trays, these trade areas. So significant damage was found, but it is in an area that they feel confident that they can monitor it. We're going to monitor this vessel over a period of time for the next 1.5 years until they actually go into their turnaround. By doing this inspection today, it helped them know what they're going to be walking into in that turnaround as far as repair plans. And the alternative would be opening it and then do a manual UT wet mag as well, and then coming up with a repair plan in the middle of the turnaround. So by being able to do it non-intrusive, we're able to provide all that insight prior to the turnaround. And then we're going to continue to monitor it over the next 1.5 years or so on probably a 3 to 6 month schedule as well.
Chase, there was a question on that about the, do we have the ability to show the depth chart?
I could, if whoever's asking that question is interested in reaching out, I'm more than happy to show more information in a one-on-one or some type of one-on-one meeting. I've got lots of really, really good examples that we can really dive into some technical stuff beyond what I'm showing here today. Other than that, I think this is my last slide here, actually. So to sum it up, robotics, mechanical rastering with the phased array, electrical scanning can provide a new paradigm shift as far as productivity. In general, it's somewhere between 5 and 10 times faster, depending on the probe setup, and a 25x resolution increase. Well, 10x on the corrosion mapping and then 25x on the high resolution trilateral scanning. This provides the AUT inspections of in-service assets full coverage with the ability to use the steerable robots, drive around on the asset. We just need to get access in one point, and then we can drive the robot around, around the asset. Rope access generally, in most cases, is not needed. We can get to most locations either just through the common decking or through a JLG access. And this overall, the production is, it overall reduces the cost of the inspection as a whole. Most times I'm seeing inspection work scopes that are in the 30 or 40 days reduced to 5 to 10 days or less. So it's very common to have it be 5 times faster in general. Also with the data density, we can characterize the damage with a really, really fine tooth, really, really high resolution, and we can provide the operator the things that he needs to be able to make confident calls and reduce false calls, reduce the false positives, and reduce the errors that commonly happen with this type of inspection that either needs follow-up required or we have missed calls that often happen.
Okay, thanks, Chase. I'll have a couple more questions here. I'll group a few of these. One is on the robotic side, any sort of temperature limitations, or how high can the temperatures be for this application, and then also what distance can the robot travel or climb?
Okay, sure. Generally, we use water as couplant, and with the hardware constraints, with the typical setup, we're constrained to 240 F. That's our constraint when using water and having a high production with what we're doing right now. Now, if we look at using other couplants, we can increase that up to about 300 or so, 320 degrees with the same hardware that we're using today. And then going beyond 300 degrees to maybe 500 degrees is much more challenging. A lot more constraints become, it becomes a little more problematic. We can provide solutions for 300 to 500 degrees, but there's a lot more planning involved and timelines that need to be adhered to like make it actually happen quickly. It's not something that we can just deploy, next day like we can with this.
Thanks, Chase. And then one other question here: Are we looking at this for H₂S and other types of hydrogen damage?
Sure. Yeah, good question. We're currently in trials right now with several owner users, labs, and trying to prove out the ability of using the high frequency version of trilateral when using 7.5 and 10 meg. Our initial inspections so far proved very good at finding stage 2 and stage 3 damage on lab samples. These are actual cut samples from the field, not lab generated samples, but actual samples from the field. Overall, the resolution is there, the detectability is there, while still retaining the high production rate of the technology. Now, the only thing is we now typically do H₂S inspections on, say, a small exchanger or a vessel, only a few square feet. Now, with having this technology and having confidence in it, we can use it to our advantage to maybe screen larger areas of a vessel, maybe do much more, provided that we can have the surface clean enough to do that.
Excellent. Any other questions from the audience? We'll hold on here for a few more minutes. That does, conclude the slides for Chase. I had one more for you, Chase. Given the amount of data that's being collected, the high resolution and the speed with which we're collecting this information, how does the data become interpretable? How is this ultimately presented to the customer?
So currently the data is put into A, B, C, and D scan, just like any other typical phased array related technology. So you can screen, maybe you used to do a couple feet by a couple feet. We can now today do 10 square feet or even 20 square feet and still look at it in those views and digest it actually fairly quickly. Overall, our plan when deploying this technology is to have the technicians in the field gather this data and then upload it to the cloud, and our level 3s and house level 3s will look at that data and turn around information about that inspection within 24 hours. So whether or not that's no findings or if there's significant findings, they're going to be providing a day by day, working closely with the customer, preliminary reports such as the ones that were shown just a couple slides ago. We can continue to scan more areas or expand the scope, add to those preliminaries, add additional information as it's coming in. and help the customer really understand the health of that asset as the inspections are ongoing. But it is fairly quick and fairly fast for us to turn that information around for the customer, provided that we have the 24 hours or so to turn that data around. As far as fitness for service, we can work closely with any engineering group. We've worked with several of them and can provide this data in a raw format, either in CSV or Excel, or through the actual raw data files that we have. We're happy to provide them to anybody that can interpret them and work with them.
Chase, one other question that just came in. What's like the smallest type of defect that you can reliably detect? I know we had talked about some of the blistering or laminations and some of the peripheral cracking off that, but what is the smallest type of defect that you could size with this technology?
Roughly 1 millimeter for our probability detection. Our sizing is a little smaller than that. But for probability detection, we can find defects that are roughly 1 millimeter in size. We calibrate this setup with a 40 thou notch, or 1 millimeter notch roughly, depending on the thickness and application. But generally, that's our detectability, is about 40 thou.
Excellent. We can hold on here just for another 30 seconds, but Chase, thank you for your time. Thank you for presenting this on this great technology, and thank you for the audience. Some amazing questions here. We'll continue to share more information on this new and groundbreaking technology. We've got an upcoming webinar with Inspectioneering down the road as well. So look out for more details, and we'd be happy to follow up on an individual basis with any of the more technical questions and deep dives that were asked here. Thanks again, everyone. Have a great rest of your day.